It's not what it means. Okay, now it's recording. I just had to hit it again apparently. Okay, today we're going to be dealing more with these intercepts. We are studying, in this chapter, we're studying the graphing of functions, the way to do it without having to punch it into a calculator. You don't have to write this down. We're just going to talk about it. Carrying you face forward. Polynomial functions. Everything we've been dealing with so far have been, well, in this chapter, have been polynomial functions. Yesterday, quadratic, all those quadratics where it was a square and an x and a number, polynomial function. A polynomial function is basically any equation where you have one variable, most of the time it's x, pretty much always it's x, not always, but most of the time. Sometimes it's t for time as your variable. And they're in just descending order, well, you can rewrite them in descending order, but it's like 3x to the fifth, 4x cubed, 2x squared, 4x, blah, blah, blah. This is a classic polynomial function. Right there. It can be as lengthy or as short as you want. Now, yesterday we were only dealing with quadratics. Ones that have a highest power of 2, a square. But they can go up as high as you want them to. Now, for it to be a polynomial function, certain things cannot happen. You cannot have a root, which is the same as a fractional exponent. All your exponents have to be positive whole numbers. You cannot have a variable in the denominator. That would be a negative exponent. Essentially, it all comes back to the same rule that all exponents have to be whole and positive. Any fractional exponent will give you a root. Any negative exponent will give you that issue. So, polynomial function basically has to have nothing but numbers and x and your one variable. That's pretty much everything about it. Let's look at some. All right, determine which of these are polynomial. And for those that are, identify the degree. The degree of a polynomial is simply the highest power, the highest exponent. Number one, polynomial or no polynomial? Yes. You don't have any x's in the denominator. You don't have any x's under a radical. Those are pretty much the only two things you have to worry about. All you have are x terms with coefficients all the way across. Ideally, they'd be in descending order, but you could just rewrite them in descending order. So, number one, yes, and it has a degree of 3. What about number 3? Yes. Yes, it has a fraction, but our variable is not in the denominator, so it's not a problem. It's the same as like 0.2x, which is the number. So we have only one variable. It's just being raised to whole numbers. Yes, that's an irrational number, but in the end it is just a number, as is 1/5. So 3 is yes, and what's the degree? Very good, 5. 5, yay or nay? No. Because you have a variable in the denominator, or x to the negative 1 power, which is wrong. 7, yay or nay? No. That would be the square root of x. 9, yay or nay? Okay, highest power is the degree. Next slide. No, Jerry. Alright, graphs of polynomial functions. The reason that we are specifying polynomials is that polynomials are just nice, fluid graphs. There's no breaks, there's no sharp edges, just nice, fluid, curvy, wavy graphs. That's the key to a polynomial. So, we're just going to be eyeballing a few and saying, is not. 11, what do you think? Polynomial or no? Yes. It is, that's right. Nice, fluid, and curvy. What about 12? No. No, there's a break. It will be one continuous function. So no. Yes. Questions about any of those four before we move on? Alright. We're already halfway done. Yay, okay. Leading coefficient test. Which is blah, 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 what I like to call end behavior. Now, you want to start up a little chart in your notes for end behavior. It's only a 4-part chart. 4-part chart. So it's going to help you big time. End behavior is what we're going to call it. And I'll start the chart with you. All right. Let me just make this a little smaller so it ain't in my way. Okay. So we're going to call this the turn on your Moby board time. We're going to call this the end behavior chart. Well, my pen's not. No, it's not. My pen's just not working. There it goes. Okay. All right. The end behavior a chart. There's only 4 possible things that your polynomials can be doing on its two ends. What I mean by its ends are the domain for every polynomial is negative infinity to positive infinity. Nothing's going to change that. That's why it's continuous. So as it shoots off to infinity, there's only 4 things they could be doing. They could both be eventually going upward, they could both be going downward, or you can have one of each. Okay? Well, think about like x squared. What's x squared doing? Up, up, down, down, up, down, down, up. Up, up. That's right. In behavior chart has only 2 things that determine what you're going to have. The first one, and they are both attached to the leading term. First off, the leading coefficient. No, it's going to be leading coefficient. Positive or negative. That's what we're looking for. Wow, I'm not going to have nearly enough room to write all this. Nope. Oh, wow. That was a fail. We'll use it right. Yes, it does. Leading coefficient. We just need to see if it's positive or negative. Now, like x squared, leading coefficient is 1. It's positive. So, we're going to go positive, positive, negative, negative. There's 2 possible positives, 2 possible negatives. The other thing we're going to look at, which I'll change colors to help determine, is the degree. Degree. This is supposed to be like 2 columns, but I'm not really writing it very well. You probably want to do it better in your notes. And we're looking for even or odd. You might want to write that out in words if you have more space than I do. We're looking for even or odd degree, which is the highest power. We're going to fill up those 2 charts, and our end behavior will come last. The third column, which is the one we most care about, is our actual end behavior. That's what we're boiling down to. So, our 2 possibilities. For positive, we could have a positive leading coefficient and an even degree. We could have a positive leading coefficient and an odd degree. I'll be showing you examples of all these in a second. We could have a negative leading coefficient and an even degree, or a negative leading coefficient and an odd degree. Those are the only 4 possibilities. Now, x squared, that's an even degree, 2, and it's a positive leading coefficient, and we said it was what? Up, up? And that's right. On both sides, the left and right, it's going up. Now, the book actually does it like this to help you better visualize. As it goes left, it goes up. As it goes right, it goes up. I just like to do 2 up arrows, but whatever. That's what its end behavior will be. And that is this one over here in their little chart. What? No. No. Would you like me to stay with my color coordination? Yeah. Fine. I guess I didn't need to do this twice, did I? Sorry. Stay with my color coordination. Even, is that better? I don't care. Okay. Now, positive, odd. So this would be something like a positive leading coefficient, odd exponent, like 2x cubed. X cubed, doesn't that come in down from the left and go up to the right? Or I guess, yes, it does. Think about the parent graph of x cubed. It looks like this. It falls to the left, goes up to the right. That is its end behavior. Falls to the left, up to the right. Next 2, negative leading coefficient, even degree. Like yesterday, we did stuff like negative 3x squared, and we knew that was going to be a maximum value, and it was going to go down, down. So these are down, down for end behavior. They're both going to go down. And the only other one left is negative leading coefficient, odd degree. Well, if x cubed looks like this, then when we stick a negative on there, it's going to flip it around and it's going to look like that. So it's going to go up and then down. All of this is just to help you be able to quick sketch graphs to speed up your little math processes during problems. That's all we're doing. End behavior chart. Those are the only 4 possibilities it'll be. It won't ever flatline in a polynomial. Just not what they do. Questions on that chart before we look at examples? Alright. Now, the leading coefficient is just the number, yes, bless you. It is just the number being multiplied by your highest power. So, what's my degree on number 19? 3, which is odd. It's odd. You know, I'll just write odd. What is my leading coefficient, positive or negative? So, positive, odd, look at your end behavior chart and tell me what it is. It goes down, and then it goes up. And this is all I need to see in your answers. You can write it in words if you'd like. It goes down to the left, rises to the right, however you want to do that. That's leading coefficient, LC. What about number 21? Degree, odd or even? Positive or negative? So it's going to be up, up. Kayla, try not to botch number 23 when I ask you. Even or odd? Even. Positive or negative for the leading term? Negative. Now, very good. Well, before we go any further, what's that going to be? Down, down. Very good. Now, when I say the leading term, do I have any that are out of order? No. What if it was written like this? 6x cubed minus 2x squared minus 7x to the 5th. Is that odd or even? Odd. Is it positive or negative? Negative, because the number attached to the biggest power is the one you look at. Now, these were always the ones in front. It won't always be like that. Sometimes you have to rewrite it yourself. So it would be negative. Very good. Questions on this slide before we move on? There's only 3 more slides. Degree of 19? Where are you looking at? Here? Oh, number 19. No. Yeah. All you do is look at the biggest power. Not when you're finding degree. No. Oh, I think I know what you're talking about. Back in Algebra 2, there was a thing where I know what you're talking about, but no, that's not the case here. Because in behavior, we're talking about as x shoots off to positive and negative infinity, right? So we're talking about as you plug in ginormous values for x in both the positive and negative directions, you know, as you get closer and closer to infinity, you know, eventually your x cubed is just going to dwarf everything else there. Because let's say you plug in 100,000. 100,000 cubed is 100,000 times bigger than 100,000 squared. So eventually, your highest power is the only thing that's going to matter as you put in bigger and bigger values. That's why that's the only thing we have to look at. All right, let's see. Find the zeros. Ooh, I knew we were going to get one of these. For each polynomial function and give the multiplicity for each zero. State whether the graph crosses the x-axis, touches, or turns around. Well, 25 and 27 are a lot like yesterday in the fact that they're pre-factored for us, which is nice. What values could I plug in for x that's going to make this whole equation equal 0? What values could I plug in for x? That makes 5 and negative 4. Now, multiplicity. What did they mean by multiplicity? Because you see how this is really x plus 4 times x plus 4? So really, negative 4 occurs twice. That's important to notice because if we were to FOIL all this out, how many x's would we have? This times this times this how many x's, what would be our degree if I FOILed all that out? There's 1x, here's 2 more. 3, yeah. You would have 3 x's. That's important because in a minute, you're going to be graphing some of these. And if you know it's 3, then all you need are your roots and your end behavior, which you would know by knowing that that's 3 and positive, and you could sketch this fairly accurately. Now, when it says that it cross or touch, if you have a root that occurs an odd number of times, this one only occurs once, that's what I'm talking about. It could also occur 3 times, or heck, you might even have one that goes to 5 or 7 times. If you have a root that occurs an odd number of times, then your graph is going to cross at that spot. It's going to actually cross the x-axis there. If you have one that occurs an even number of times, 2 times, 4 times, 6 times, whatever, then it's just going to touch and turn around. So here's what, I'm not asking you to sketch these yet, but in a second I will. What? Odd crosses, even touches, yes. That might be something y'all want to add in your notes. So here's roundabout what this sketch would look like. End behavior, positive odd, down, up. I'm not even going to worry about my y-intercept right now. Let's see. I know it crosses at 5 and touches at -4. So if I asked you to sketch this, this is what it would need to look like. Come up, touch, cross. Boom. There's the sketch of that function. Touches at -4 because that occurs an even number of times. Crosses at 5 because it happens an odd number of times. And your end behavior from your end behavior chart. Yes, sir.
Okay, so whenever you're finding the even coefficient, whichever it is.
Well, I kind of cut a corner there. Normally, like it'd be 1 and 1 for these two. You would need to FOIL all this out and then look at your leading term. Okay. I happen to notice, just because I've done these a lot, I wouldn't ask you to notice this kind of thing early on. If you FOILed all this out, your leading term would be 2x cubed. Oh, that's what it would be. And I happen to know that already. But we're going to be working more with that stuff. But this is just an example. Good question. 27. What are my roots? 3. 3 times, right? So, states, just if you list it like this, if you list it like that, then you've already taken care of your multiplicity. Okay? If you were to only list them once, then you would need to do this for your multiplicity. -6 happens 3 times, 3 happens 1 time. But if you just write it out like this, you've both listed your zeros and given me the multiplicity. So that kind of takes care of both of those steps. Okay, at 3, is it going to cross or touch? Odd crosses, even touches. So at 3, it's going to, and -6, it's going to. Oh, good, because they're both odd. And that's all for those. You just write that. 3 crosses, -6 crosses. Gotcha. Now, 29 and 31, those are harder because we can't just say, oh, it's 3 and -6. You're going to have to do a little factoring today. You're going to have to do some factoring. For 29, what can I factor out? X, which leaves me with x squared minus 2x plus 1. Now, if you notice that, you have 2 options now. If you like to factor, then by golly, just factor that thing. If you don't, you can punch this thing right here, just this piece, into the quadratic formula. It is now a quadratic equation, and you can find your 2 roots that way. We've been factoring since, for who likes to factor, who's already noticed the factors of these? Who's already factored this? Alyssa. X minus 1, x minus 1. Okay. Let me just show you very quickly how you could have done this. If you don't like to factor, if you can get it down to a square, all you would have to do is, I'm taking this equation right here. Negative b plus or minus b squared minus 4ac all over 2a. So that's 2 plus or minus 4 minus 4. 2 plus 0 over 2. And 2 minus 0 over 2. And what are both of those? 1, which we found by factoring as well. So you can do it either way if you get it down to a quadratic. So let me actually answer this question now, but I haven't left myself any space. The roots are 0. Whenever you just have an x that factors out, that is a 0 root. That's the root that it gives. 0, 1, and 1. Zach's going to cross or touch at 0. Very good. Drake's going to cross or touch at 1. Very good. Questions on that one before we move on? This, what I wrote in blue is all you have to write. I was just showing that you could find them both ways. Who can tell me how I'm going to work number 31? What's the trick to 31? 4 terms, leading one to cube. Whenever you see that, your mind should instantly go to factoring by grouping. Very good. Yes, even crosses, odd touches. Not if the number's even, but the number of times it occurs. Okay? Alright. Alright, so factoring by grouping. I'm going to group these two. Now when I group these two, what's something I need to make sure I remember to do? Right. That's now a plus because I factored a minus out of the whole binomial. Okay, Heath, what factors out of the first pair? And another x, that's right. Leaving me with what? Very good. What factors out of the second group? Excellent. Leaving me with? Very good. Well, I'll move it down a little bit, but I won't take it off. Jordan, how do I rewrite this? Gave you one of the hard questions. All right, who can help him? I mean, how could I rewrite that? Well, remember, this is the same thing. If I had like 3y minus 2y, you have a common term, so you would just take 3 minus 2, right? Common term, so I just subtract x squared minus 4 from each other, just like I would 3 minus 2. And then I bring along my common term. Does this factor any further? Yes. Again, if you don't like the factor, look what we have here. Quadratic. Punch it into the quadratic equation if you want to. Your b value would just be 0. But that does factor. So Josh, take us home. What are my 3 roots? 2, negative 2, and negative 7. And this one, cross or touch? Cross. It only happens one time. This one? Cross. Cross. They all only happen once, so they all cross. Oh, okay. Good question. Well, what's my leading term here? What's my end behavior going to be for number 31? Let me erase all the stuff I drew on it. Somebody look at your end behavior test or chart and tell me what my end behavior is going to be. Odd positive. Odd positive. Down, up. Very good. So it's going to cross at negative 7, which I'm just going to eyeball to be there. Negative 2 and positive 2. So it's going to come up, cross, cross, cross. Ish. Questions? Now that's just a sketch. That's not accurate, but the behavior and the roots are accurate. All right, only 2 more slides. Use the intermediate value theorem to show whether each polynomial has a 0 between the given integers. This is a very basic concept. Drake, I'm going to ask you a question. Now, it's going to be kind of a outside the box thinking question, okay? If I have a graph that crosses right here, right? What is one conclusion I can make without knowing the exact numbers? What's a conclusion I can make about a difference between this y value and this y value? It will be less than. And what's an even more specific difference between them? A more obvious difference. Positive and negative. Whenever you have a root, on either side of that root, you should have one positive y value and one negative y value. Anytime you cross that axis, that should happen. So the intermediate value theorem simply says you can find out if there's a root between these two numbers, like it's 0.7 or something, by plugging those two numbers in. If one of them gives you a positive y value and the other gives you a negative y value, you have to have a root in between. That's the only way you can get down there, is by crossing. So that's all we're doing. We're looking for a sign change. So here we go. Now you could do this on a more basic calculator, but since I've got this one on my desktop, I'm just going to go ahead and use this one. Okay, so I'm going to plug in 1 first. Well, I can probably, actually, I don't want to get in the habit of using that if I'm not going to let you use it. 1 cubed minus 1 minus 1. Is that positive or negative? Negative 1. It is a negative number. Let's plug in 2. 2 cubed minus 2 minus 1. What's that going to be? 5. Is there a sign change? Yes. Negative, positive. Yes, there is a root between those two numbers. No? Oh, I don't know. You might. You might. I don't know. I haven't looked at that slide yet. Here we go. Next one. Negative 1. Negative 1 to the 4th times 2 minus 4 times negative 1 squared plus 1. So that's 2 minus 4 plus 1, which gives me what? Negative 1. If I plug in 0, which I'll do right up here because I'm out of space, that'll be 0 minus 0 plus 1. Positive or negative? Is there a sign change? Yes. One of them was negative, one of them was positive. And that's all you have to do on that. When I give you one of these on the test, I will do my absolute best to give you one that's not horribly, like I won't give you one that's like 7 and 6 since I'm not letting you use the scientific calculator. I'll give you one with like 1 and 0, so it'll be easy to plug in. Right. But since these are assuming we can use a calculator, it might be easiest to find some of these values by punching it into the calculator, so I would do that. 37 or 39. Does anybody want to see either of those work? Just plugging them in, looking for a sign change. Last slide. Last slide. Oh my goodness. If it's any consolation, I do believe that I put every other even for that section. So you don't want to be doing like 2 or 3 of them. But we still have to do them. So here's all the things they want us to do. Determine the end behavior. Find the x-intercept, which is basically find the root. Find the y-intercept, which is actually the easiest part. I don't know why we haven't done it yet. Determine whether the graph has symmetry. You can just do that by looking when we're done. I'm not going to make you do it right now. Although, does anybody remember the key to this on D? We did a section about that. In fact, later I referenced that section incorrectly with something else. But we did do something like this. There's actually a really quick way to tell if it's going to be either of those symmetries. Anybody remember what that was? It was even or odd. Yeah. Any function like this one that has all even exponents is going to have y-axis symmetry. Any of them that have all odd exponents, like this one, is going to be origin symmetric. And if they have a mix, they'll be neither. That's a quick way to do it, but I'm the least concerned with that step. And then E, you're going to graph. And it says if you need to satisfy your soul and have a more accurate graph, you can find some additional points. I'm not going to. Let's look at one. Good idea. Okay, here's the thing. Any polynomial function. Here's a classic polynomial. If a polynomial function has nothing more than x's and then one value at the end, possibly without an x, the y-intercept is always going to be the number at the end. Because if you plug in 0, which is what a y-intercept is, it's going to be 0 plus 0 plus 0, and then that number. So, like 41, the y-intercept would be negative 2. Okay, these are interesting because I actually think they get easier the further down you go. Because the further down you go, you can more easily pull out your root. You still might have to FOIL it to find your end behavior and stuff like that. So I'm actually going to do one of the last ones, and then I'll come back and do one of the first ones. Let's see. How about I just go all the way to the bottom? Number 63. Here we go. Well, let's do the easy part first. You don't have to do these in order, but I will go ahead and list all the things it asks us to find. Leading coefficient. It asks us to find the x-intercepts, the y-intercept, and then to graph it. So that's the stuff. Oh, and symmetry. Okay. In this form, which of those things is the easiest to find? X-intercepts. And what are they going to be, Drake? You gave them to me in numerical order. You have no idea how much that means to me. Very good. Negative 4, 1, 2, and 2. Negative 4 is going to make this one 0, 1, 2, twice. Very good. Very, very good. No, but it does mean I appreciate you. Okay, now, the safest, yeah, we're just going to do it. You have to FOIL. That's going to be probably the most tenuous part of these problems is when you FOIL these. So, first thing I'm going to do is FOIL this piece. Now, I know you guys have FOILed till you're blue in the face by now, so I'm going to kind of skip a few steps just to get to the answer. Oh, it's nothing but FOILing, though. X minus 2 squared, x minus x squared minus 4x plus 4. When you FOIL this guy, you get, I don't care how you do it, by the way. I just like to group them. But you can do it in any order you want. Multiplication is a commutative process. Okay, so that'd be plus 3x minus 4. Ooh, look, I get to do 2 trinomials. Ugh. Okay. Brace yourselves. Put your pencils in the upright position. This is going to get bumpy. X squared times all 3 of those. X to the 4th minus 3x cubed minus 4x squared. Negative 4x times all 3 of these. Negative 4x cubed minus 12x squared plus 16x. Take the positive 4, multiply it by all 3 of these. Yeah, that's fun, isn't it? 4x squared plus 12x minus 16. Like terms time. X to the 4th, and I'll mark through them after I'm done with them. Let's see, I have negative 3 and negative 4, so that's negative 7x cubed. Done with those two. I have negative 4, negative 12, and positive 4, which all add together to get negative 12x squared. 16 and that's 12. What's funny about all this is that's my finished product. Only thing I need here is my first and last term, really. And I'll show you a shortcut to finding that if you'd like in a second. But, so, I put leading coefficient. This should have been end behavior. That's actually what I need. End behavior. Who can look at this and tell me what my end behavior is going to be?
What's that last red number on that?
Right here? 12x. My end behavior is going to be what? Up, up. It is even and positive. Up, up. What's my y-intercept going to be? Negative 16. What kind of symmetry is this thing going to have? Even, odd, or neither? Very good. And we're ready to graph. We're ready to graph. Before we graph, let me just show you. If you want to avoid the extensive FOILing later, something you can do. Since you only need the first term and the last term, here's one thing you could do. Actually, I'll tell you what. I'll just do it on the next one rather than show you multiple steps. I'll just do that on the next one. Okay. Let's go ahead and just graph this puppy and be done with it. All right, so let's plot everything we got. In behavior is going to be some kind of up, up. It doesn't have to be pretty, people. Y-intercepts, negative 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 60. Okay, right here. X-intercepts, negative 4. 1, 2, 3, 4. 1 and 2. Are there any of these x-intercepts that are not going to cross? Which one? 2. Very good, because it happens an even number of times. And here we go. I'm going to come down, cross, go through my y-intercept, cross, touch. And that is a sketch. And that's as accurate as I need for you to be. I've gone through negative 4. I've gone through positive 1. I've gone through my y-intercept. And I've touched positive 2. And I've gotten my in behavior. But I'm going to stop. I think we could agree the only really long part of this problem is the foiling, and I'm about to show you a way to get around that anyway. Questions on that one? About what you're doing, how it is something, anything like that. I will tell you this, and I'm not trying to be mean about this. This is an excellent test question because rather than me using 5 questions to ask you to see if you know in behavior, y-intercepts, x-intercepts, and all that stuff, this question covers all of it. So there's a good question that on your test, there will be a polynomial like that with 4 graphs, and it'll say which one's the correct graph. Because it has so many things. So, be warned. Any questions on that one? Okay, I'm going to look at one more of these prefactored ones so I can show you that quick little shortcut, and then I'll do one of these longer unfactored ones, and we'll be done. All right, number 61 looks pretty good. Now, if you do, darn it, if you do not like to do all that foiling, here's a shortcut you can take. First thing, I'm going to go ahead and list the things I'm going to need to find. In behavior, x-intercepts, y-intercepts, symmetry, thank you. And that was it. Okay. First off, what's the easiest thing to find here? X-intercepts. Denton, can you tell me what they're going to be? Positive 1. You have to look at what's going to make this equal to 0. So 1 minus 1. So it'll be positive 1. How many positive 1s? Very good. What would this one be? And, well, what if I covered all this up? What could I plug in for x here that's going to make that equal to 0? If I plug in 2, that's just going to be q cubed times negative 2. 0. Whenever you have an x that's not being added or subtracted to something by itself, it's just 0. And how many zeros? 3 of them. Very good, because it's cubed. Now, here's the trick if you don't like to FOIL. Since we're only interested in the first term and the last term, don't write out any of your binomials that are being raised to a power, write them out like this. Okay? Now, since we only need the first term and the last term, here's what you can do. Multiply this and just your front terms. Negative 2x cubed times x times x times x. Negative 2x cubed times x times x times x will be negative 2x to the 6th. And if there had been like a 2 in here, you would need to multiply that too, but there wasn't, so never mind. Dot, 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 dot. Now take this and multiply by all your last terms. Negative 2x cubed times negative 1, which will make it positive, times negative 1, which will make it negative, times 5, which will make that negative 10x cubed. That will be the last term. Now, what's the y-intercept going to be if our last term still has an x in it? What's our y-intercept going to be? 0, right. If there's no number at the end, which this one wouldn't have, it'll just be 0. What's my end behavior going to be? Austin, am I even or odd? You can look this up. My degree, is it even or odd? Is it positive or negative? Even negative, what's it going to be? Down, yeah, very good. Now, this one, I could easily tell right here that it's going to have what kind of symmetry? Neither, because I have an even and an odd. I guess the one thing you might need to do some foiling is, if you were to have gotten a 7 here and a 3 there, I guess you would have no way of definitively knowing, unless you're really good, if you're good at visualizing and stuff, of knowing whether they'd all be positive or all be even. I mean, even or odd. So you might have to actually foil to see that. But since that's the part I'm least concerned about anyway, I don't even care if you do that. Eyeball it from that first and last term if you want to. Alright, so, neither. And we're ready to graph. I know. These can feel a tad overwhelming. So, into behavior. Down, down. All the places I'm going to cross. I'm going to cross at 0. That's both my y and my x-intercept. I'm going to cross at -5. And I'm going to touch at +1. Here I go. Cross, cross, touch. It's not pretty, but there it is. Cross at 0. Cross at -5. And touch at +1. Well, I went over a little bit. But question. This is one of those lessons that feels easy, feels easy, feels easy. Holy mackerel. We'll just briefly look at one of these that's not pre-factored for you. 43. Okay, that's the one you want to look at. That is 41. Hola. Got it. Alright, 43 it is. Well, here's the thing. 43, what could you factor out really quickly when you start factoring that? X squared. And when you factor out an x squared, you'll be left with a quadratic. So, yeah, let's look at 51 might be a tad harder. Let's look at 51. What factors out of that thing? Well, yeah, let's go ahead and let's pull out what we can first. Let's see, we have our end behavior, our x-intercepts, our y-intercept, and our symmetry. Now we can find 4 of these right now. What's going to be my end behavior? Somebody just raise your hand and tell me. Save time. Odd, negative, which will make it what? From your chart. Up, down. Very good. Up, down. Okay, we're going to have to come back to x-intercepts. That's the one thing we have to come back to. What's my y-intercept going to be? Is there a number here without an x? So it's 0. Symmetry, origin, y-axis, or neither? Origin, right. Odd functions, ones that were all odd, are origin. Now when you're sketching this, it might not look perfect that way, but that's what it should be. Now to find our x-intercepts, we have to factor. What factors out of here? X. Leaving you with 6x squared minus 9 minus x to the 4th, which I'm going to rewrite in order. Oogly, oogly. Does anybody remember the trick to factoring when they're going down by the same interval every time? What are they going down by? Are my exponents here, 4, 2, 0? What are they going down by? 2's. So you could factor this the exact same way you would a normal quadratic, except it's going to look like this. Instead of just an x and an x, it'll be x squared and x squared. And what's going to go in here? What multiplies to get negative 9 but adds to get negative 6? Or even is there one? What was it? That's going to give us a positive 9, unfortunately. Is there one? Are you serious? They gave us one without an easy factor. I was hoping I had something that was going to look really ugly. So, negative. Now it can be negative 3 and 3. Man, that's still really ugly. I can't believe they did this considering we're not. Yeah. Oh, I'll look over the ones I assigned for you in your homework to avoid you having this kind of factoring problem. Okay, now you could do quadratic for both of these. Whenever you're missing your b term, you could also just solve both of them for 0. Solve both of those for x, and that's another way you could just find your root. Either one you want to do, that's cool. Add the 3. Let's do this one first. Oh, good sketch. Thank you. Thank you. Plus 3. Okay, so if we add the 3 to the other side, take the square root. So that's going to be plus or minus square root of 3. For the first one, I'm just setting this piece equal to 0 and finding what's going to make that thing. Or you could have done quadratic, whichever one makes you happier. This one, there'll be negative x squared equals negative 3. Multiply both by a negative 1. And that will also give us plus or minus square root of 3. So what are my x-intercepts? What's this one going to be? 0. And then I'm going to have negative radical 3 how many times? Twice. Once here, once here. This is by far the harder one than you will probably see, by the way. So if the factoring thing seems a little rough, it won't usually be this hard. If that's comforting. And then positive square root of 3 and positive square root of 3. Yay! It's going to cross, touch, touch. Let's quick sketch this thing and I'll cut you guys loose. Here we go. In behavior. Right. It's going to be up and down. I'll switch colors so it doesn't blend in. Up and then down. It's going to cross at 0, both for an x and y intercept. And it's going to touch at negative square root of 3 and positive square root of 3, which are like 1.6 or something. So, come down, touch, cross, touch. And you can kind of see how it's symmetrical around the origin. Yay, that was fun. Okay. I'll put that back on the board in just a minute if you want, but here are the problems.